Hello everyone, welcome to the OneClass channel and good morning. My name is Fajiro Rome and I'm an Honors Bachelor of Science graduate currently working towards medical school. Today we'll be going over some commonly asked questions both at the high school and college level. If you're looking to get some just extra help or an extra hand in regards to these topics, please check out the links in the description below and we'll be more than glad to help you. Okay? Now, with the formalities out the way, we're going to begin our session for today. This is going to be with the first question being, depict the electron configuration for phosphorus using orbital, box, and noble gas notation. Give one possible set of 4 quantum numbers for electrons beyond noble gas. So this is definitely a bigger scope of a question. Nonetheless, we will tackle it right away. So the question asks for phosphorus, okay? So on the periodic table, phosphorus is the 15th element, okay? So I'm going to go ahead and start writing out our electron configuration numbers. So we have 1s, 2s, 2p, 3s, 3p, 3d. I'm going to stop here at the 4s because as you'll see for phosphorus it doesn't even get past 3p. But how do we count this? So hydrogen and helium, okay, because helium is the only exception, even though it's a noble gas, it counts as being on the s orbital. That will be clearing your 1s. So we're done with that. We actually at least have 1s2 because hydrogen then helium. Then 2s, okay, 2s1 is lithium, 2s2 is beryllium. Okay, so we've cleared through that. We're in a sense counting through each element. Okay, and then following after we have boron through neon. Okay, these starting here from column 13 through 18, excluding helium, that's your p orbital. Okay, so because it's a second row, we have 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. So we've cleared that row. Then we hop to the next row, the third row. Okay, we have sodium, magnesium, that'll be your 3s2. And then we finally get to close to where phosphorus is. And similar to what we just did for the earlier row, we have 3p1 on aluminum, 3p2, and 3p3 for phosphorus. Okay, so this is where we stopped. Alright, and this right here is your electron configuration for phosphorus. Now if you wanted to get the noble gas notation, what you would do is this prior part, if you notice, that actually accounts for neon. So you'd replace that with this type of notation here, allowing you just to write what comes after. And this is your noble gas notation. As you can see, it makes it quite distinct which your valence electrons are. Because considering phosphorus is on the 15th column, you can see here that it indeed has 5 electrons in its valence shell, based on the fact that the superscripts here, 2 and 3, that adds up to 5. That's where you get the value from. So this question doesn't only ask for that, but also the orbital box notation. So for this, what we do is because they want to know orbital box for the whole thing and the noble gas, we're going to first draw out our boxes. Okay, so just as how I have that above with this breakdown, it's going to be the same thing, but as you notice, I'm adding more boxes here because as you're counting, you see that the s orbital had 2 elements each time, right? That's because it counts for 2 electrons. As you go to the right on the periodic table, you're adding electrons, right? So this is your S shell. Same with these, but this will be significant of your first row, second row, and then we have the third row. So like this. Sorry. We have like that, okay? And then we're also going to add the shorthand version with the noble gas. It's going to be similar to the 3 we have there, but exactly just going to start like that. Okay, and it's just going to be 3s because now we still should indicate at least what what row we're on. Now let's start actually filling these boxes. So for 1s, as we discussed, it goes hydrogen, then helium. Okay, that's how you fill that up. And then we have for the 2s, we have the lithium and beryllium, I believe. Yep, lithium, beryllium. And then to clear this row, the way it gets filled up is like this. It goes boron, carbon, nitrogen, then oxygen, fluorine, neon. You see how I filled that up? That's because each subshell likes to be half filled first before it fills up completely. Same thing here. We have the 3s representing the sodium and magnesium, and then, as you probably guessed it, aluminum, then silicon, then phosphorus. Okay, that is what we'd have. So with that being said, this neon would just reflect, this shorthand will also just reflect what's above. Okay, so we'll now be able to draw out our orbital box notation as well. So now it asks us to give one possible set of 4 quantum numbers. So the 4 quantum numbers they refer to, okay, are n, which represents your number of the shell you're on. So, well, the row pretty much, which is the number of orbital. Okay, so right now, if they're asking for electrons beyond the noble gas, as you've noticed, they all have that same number 3, okay, beyond the noble gas, because now we're dealing with electrons in the 3rd orbital, the 3rd shell. Okay, so that means for all of these here, we're actually going to be extra and just list out every possible combination of every electron in this. So because there's 2 in there, there's 1 in here, n is going to equal 3 for all of these. Okay, and now L is the type of subshell. Okay, and what I mean by that, they go through rules. Okay, if L is equal to 0, that's the S subshell, you know, the first 2 columns. If L is equal to 1, that's a P subshell, which is columns 13 through 18, excluding helium. If L is equal to 2, that's your D subshell, which is columns 3 through 12, okay? And if L is equal to 3, all right, that will be your F subshell, which is your lanthanum and actinium series. And as you notice, okay, is that typically the N, the number of orbitals, will always be at least 1 greater than your L. Because, for example, hydrogen, okay, it's in the 1st orbital, but that means because they only have the S subshells there, you're only dealing with 0 at the L. So, with that being said, for these, the L's here would be 0, 0 as well, and here would be 1, 1, 1, because these 3 here are in the P orbital and these 2 here are in the S orbital. Now ML is possible combinations. Well, instead of putting that can be a little bit abstract, it's going to be positive and negative of L, okay? So in this case, all right, because L is 0, ML, okay, it's going to also be 0, because positive and negative of 0 is going to be just 0. Now here, okay, we want to list out all the positive and negatives. So we're going to assign them, and it's up to you how you want to assign them. I'm just going to start like this. So ML here for me will be positive 1, okay? Here, ML will be 0, because you want all positive combinations, so it does include 0 as well. You want to go from the negative to the positive value of L. So here, if you probably guessed it, ML will be negative 1. So we have positive 1, 0, and negative 1, okay? And for the last one, okay, MS is just type of spin, okay? And it could only be represented by positive 1/2 or negative 1/2. And typically we represent the arrows pointing up as positive 1/2 and the arrows pointing down as negative 1/2. So with that all being said, our MS for this, considering that we're referring now to the first electron here, will have that positive spin theoretically, okay? Our MS here will have a negative spin because it's pointing down. And as you notice, all these ones here in the p orbital are pointing up. So all the MS's here would be a positive 1/2. Okay, so I know they only asked for us to list one, but the key reason why I listed all of them is because if you notice, right, is that if they were saying list something from the p orbital in terms of their I always forget the word, the quantum number, it's key here to recognize that if it was in your p orbital, you would not have a negative spin for phosphorus because that is how it's structured, okay? So I believe this covers everything the question is asking for. We did go through quite a bit, but hopefully you're able to keep track and understand how we're able to work through each value. So let's see how we did. So first of all, we have the electron configuration, which we were able to do, both the long and the shorthanded version, which is good. And then we have listed now 4 possible quantum numbers, okay? 3, 1, 0, plus 1/2. So they're referring to this one specifically, 3, 1, 0, plus 1/2. This is a possible set of 4 quantum numbers. If for some reason you were given like 3, 2, that is not a possible set because we do not have a D subshell in phosphorus, okay? So with that being said, this is correct. And we're free to move on to the next question. Okay. So question